carbon that is sp3 hybridized and it has 4 different attachments. That is the beginning. Okay. A carbon that is sp3 hybridized and has 4 different attachments is called a chiral carbon. I don't know if anybody got that from the movie. Yeah? Maybe not, maybe yes. Alright, so that's the first thing. So this is called chiral. The word chiral comes from the Greeks, actually. Chiral. And sp3 hybridized carbon. With 4 different attachments. Okay? When a carbon that is sp3 has 4 different attachments, and you go ahead and you decide that you're going to put here a mirror, and so here comes my mirror, so there's my mirror. Anything provided that there's a mirror will have an image, and that image is going to look just like that. So that's the mirror and that's the image. If you take that image up and you try to superimpose onto the molecule, always you will see that 3 superimposed, your carbon, the hydrogen, and the red ball, but 2 didn't. If they don't superimpose, right, if you have an image, so you have 2 molecules, and you have that image, and that image does not superimpose in any possible way, turn it, whatever, and you will always end up with 2 that don't match. Now those don't match, but these did. Now the greens and the blue match, and these didn't. Okay, the relationship between this guy and this guy is said to be enantiomers. And enantiomers are compounds that have everything is the same. Everything is the same. They have the same connectivity. They have the same name. They have the same name. They have the same boiling point. They have the same melting point. The only thing that they do differently is that if you put it in a polarimeter is something that takes light and passes light. One is doing a clockwise rotation, and the other compound is doing a counterclockwise rotation. And that's it. But that's the difference between wintergreen and caraway. Okay, so you can have the exact same compound with one chiral carbon doing different things, and you would have 2 different tastes. They're super critical in biology. These guys are very critical in biology. I don't know how many people have taken Bio 2, which is the glow. Has he talked about chiral? Has he talked about, the selectivity of molecules? So we're going to look at it from an organic chemist point of view. We like to name everything, okay? And in naming everything, let's start with this something else that he mentioned, which is a Cahn-Ingold-Free law. I think the lights are better if I turn this off. So, I don't know, maybe you're seeing well. Perhaps it's me, but I don't see that. Oh! You think it was better before? Okay, it was better before. Alright, so if we continue with this, we come up with another layer of nomenclature. Okay, and that new layer of nomenclature, let's see if we can tell. So, white, the white ball, white is hydrogen, green is chlorine. Okay, I'm going to say that blue is bromine, and I'm going to say that red is iodine. Can I say that? Alright, so I'm saying that. So if that is true, what would be the name of this compound? If that is true, what is the name of this compound? Exactly what she's saying. You look for the longest continuous chain. Okay, 1 carbon. So that's methane. Okay, you started to take all of these things, so this guy is going to be called bromo. I heard bromo. iodomethane, right, like that, you're not going to get all the points for that test now.
The RNS.
I know, yeah. So for this one, that will be all you're going to get. It's, if it's 3 points, you're probably going to get just 1, okay? Because the moment that you recognize that the structure is chiral, you have to assign the absolute configuration. Absolute configuration is a man-wave absolute configuration. When you hear the word absolute configuration, all you hear is R and S. R is a clockwise rotation, and S is a counter clockwise rotation. And this is all of us agreeing on what we're going to do. Okay. So the next thing that we do is that we assign priorities. Right, so I'm going to go ahead and draw the structure, and I'm going to assign priorities. So I have at the top, which is red, I have iodine. To the one side, it's blue, which is bromine. To the front, I have a green one, which is chlorine. And to the back, I have a hydrogen. Does everybody see what I do? The top is in the top, which is red, is iodine. The blue, which is to the front. Okay, so we have it like that. Red is iodine, blue is bromine, to the front is chlorine. Okay, so that's the model. By convention and by the Cahn-Ingold prelogs, you assign priorities to these atoms based on the atomic number. Okay, so now this is based on atomic number. The higher the atomic number, the higher the priority. Iodine is 53, I'm going to give this guy number 1 priority. Bromine is 35, I'm going to give him number 2. Chlorine is 17, this guy is going to be the number 3. Hydrogen is 1, I'm going to give guys number 4. Okay? So that's how we organize it. If you go to a, so that's how it's atomic number, atomic number. This is all atomic number. Okay, now also by convention, it says you're going to go ahead and you're going to hold the atom by the lowest number. So like I'm here, and hydrogen is the lowest number, and I'm going to go ahead and hold the molecule like that, and I'm going to put them all like in your face. You know that guy on channel 2 or channel 4 or whatever? In your face. That's what you want to do. It's in your face. And then you're like connecting the dots. I was iodine, bromine, and chlorine. I'm going like that, and like that is R. So then this guy comes over here, and you're going to give it also the letter R. So then that name became R-bromo-chloro-iodomethane. Yes? Just they go, will you always be that perfectly organized that number? And I said, of course not. You know, so in that case, so what you do is that we're going to have to come up with a way that we can maneuver this, right? So if we continue with this, then it's, and we had it like that, I don't know which one it was, oh, it was this one. Everybody see that this one that is going in that rotation and that is R? It's an enantiomer, the mirror image. Can everybody see what's happening? Everybody sees that it's going the other way? You see it, that it's going the other way? Right, so it's going the other way. So I think the only thing that I really would like to do at this moment is to go ahead and make sure that we introduce several ways of drawing this, and you deciding by looking at your periodic table if it's going to be RRS. So we get really tired of that, and it becomes becomes really easy for me to just put that on my drawing tool. So very quickly we start switching what we do, and we do something like this, you know. So we start going a little crazy, and we put stuff like that. So just for fun, we'll do one more that seems to be easy. And your job is to put numbers on your paper. 1, 2, 3, 4, or whatever. So you're just putting numbers on your paper, hopefully. By looking at the periodic table, obviously. Yeah, tell me the numbers are over there. No, you don't have it. You go by direct connectivity. I am bonded to the hydrogen. The hydrogen is always the lowest, by the way. Hydrogen is always the lowest. There's no one below 1, and hydrogen is 1. And then I look at the direct connectivity. Bromine, oxygen, or nitrogen, right? Bromine is element number 35, bromine is 1. I look at oxygen and nitrogen. Oxygen is element number 8. Nitrogen is 7, so this is 2, and then this is 3. And then I do this. Then I just cover that guy up, and I'm doing this. Oh, I'm going that way. Kind of like driving a car. I'm going that way, right? And that way, yes, I'm making a right turn. So then this gets the letter R for the rotation. Yeah? All right. Continuing with the same examples. And I have that. And we're still numbering. Okay? You are still numbering. So okay, so I'm going to give it numbers. So this is a 4. Hydrogen is a 4. The iodine is going to be the number 1. Chlorine is number 2. The OH is number 3. By convention, you cannot assign it just yet. You have to rotate, and you have to put number 4 in the back. And in the back is the dash. So at this moment, you cannot assign RNS until you physically or in your head can figure it out. I can't. At this time, I give up. Okay. So what I'm saying is this. This is showing the molecule like that. Right? This is showing the molecule like this. So what we're saying is you hold 1, bless you. You hold 1, so the molecule is looking like that. Is everybody? Let's say the molecule is looking like that. The lowest is to the top. You hold on to 1, and then you spin to put the hydrogen to the back. And then you hold, you turn, and you assign. Okay? But we have to do this on paper. Yes, everybody, we have to do this on paper. We don't have the little molecules with us. So on paper, I can go ahead and now I make my life easier. Everybody, I'm going to make my life easier, even though some of you are looking at me like perhaps I want to think of something else. Okay, so I'm going to use the red numbers to help me out. And I'm going to say that I'm going to hold on to 2. Everybody, I'm going to hold on to 2. I already went through all that trouble. I'm going to hold on to 2, and I'm going to rotate. Okay? That 4 is going to go now to that position. Right? So I will rotate. The 4 became at that spot. What happened to the 1? Where did the 1 go? The 1 went to the wedge. and then the 3 went to the top. Do you guys see it? Yeah? Is everybody seeing what we're doing? And now, you're just going that way. Right now you look like you're going this way. You're going that way, that way, that way, that way. This is then S. Okay? Yeah? Let's do another one. Let's just go ahead and do another one and see what happens here. Yeah? Alright, sorry, she wants to look at this. So, after years of teaching this, okay, after years of teaching this for so many times, one of the things that I figured out is that a long time ago, that what you need to know is have the background of the information, and then you need to really own it. And the only way to really figure this out is by you doing. So I'm putting layers today and Wednesday, and then we're done. So we come back the following Monday. It's a dry lab. Lots of websites for you to do, lots of hands-on molecules for you to do, and that will be the only way to figure this out, right? And so you really have to try to visualize it. Let's try another one again. Okay, so my other one looks like this. We're still not naming anything, right? So we're still not naming anything. They're asking you to name the compound. Right, so go ahead and they ask you to name the compound. Well, what is obvious in naming this compound? Do we see how to name this compound? Do we see how to name this compound? Well, we would follow the same rules of naming compounds that you've done before, right? You would look for the longest continuous chain. And I think it's going to be this way. So that will be your carbon 1, carbon 2, carbon 3, carbon 4. And on carbon 2, I have a bromo. So actually, this could be 2 bromo butane. Yeah? But when I look at that carbon has 1, 2, 3, 4 different groups around it. That carbon then is said to be chiral. And as chiral carbons, we use a little asterisk that also denotes that a carbon is chiral. So the moment that you see that that carbon is chiral, and you already know it's 2-bromobutane, you are expected to then show the absolute configuration. Is it R or is it S? That's what you're looking for. Is it R or is it S? And then we take a look, right? We take a look. So it's easier to go ahead and give them priorities. We already know that hydrogen is 4. We already know that bromine is the highest atomic number. And now we're dealing with 2 that have carbons. So everybody, so both of them have carbon. This is direct connectivity, okay? And with this direct connectivity, we play the game like this. I have a carbon, so I'm attached to a carbon. I'm attached to a carbon. But this carbon has 1, 2, and this carbon has 1, 2 hydrogens. Is everybody so far the same? So far they're the same?
There's 3 hydrogens.
3. When I go to the next attachment, you have a 3rd hydrogen and you have a carbon. Is everybody seeing how we're going to go? So it's like we're going to go down the road to find the first difference. Is everybody down the road? There was a carbon and a carbon. I was bonded to a carbon, the first carbon, and a carbon. That was the beginning. And I was bonded to 2 hydrogens, and you were 2. Right? So that was how I started that. So far, that was the same for the methyl and the ethyl. But when I continue, all you had was a hydrogen, what you had was another carbon. That's when you saw the first difference. That ethyl has higher priority than the methyl. So then that guy became your number 2, and this one becomes your number 3. That's the way to do these things, to find that first difference. And then go ahead and hold and spin to have the lowest in the back. Hold and spin to have the lowest in the back. So you can hold anyone. I'm choosing to hold number 3. Is everybody seeing that? Every time I'm choosing something differently. And I'm not gonna get creative, because every time you get creative, you make mistakes. You, I, everybody. So I'm leaving the same drawing. Is everybody understanding what I mean by that? I'm gonna leave the exact same drawing. I'm pointing to the right. So nothing has changed, just my numbers. I'm holding 3 at the top, and then I'm gonna spin, yeah? And I'm actually gonna spin that way. I'm gonna spin that way so that my 4 that is on the wedge goes on the dash. Is everybody okay? I just wanted to do that spin. And the moment that I did that spin, the CH2, which is number 2, goes to the wedge, and the bromine went to the solid line. When I try to do the orientation, I cover this guy up, and now I look that I'm going this way, and that way is R. So when I ask you to name the compound, you're going to come over here, and you're going to start out by this. R, 2-bromo, butane. Okay, so the only thing that you really have to do, okay, you really, by convention, this was man-made, so this is not, this is man-made. By convention, you will name the compounds using the lowest, having the lowest priority always on the dash, in the back. If you can figure it out in your head, you don't have to do any of this. I'm just putting this all down so that you can see it. Once you get to be this fast, you don't have to do this, right? We're just creating that beginning of how we're going to do this so you can figure it out.
When it comes to larger compounds, like the ones that we name first as water,
Oh God, can you imagine? She goes, are you really ever? She goes, you know that third question on the test or whatever, the one that you have the 1-cycloprogol, the 3-cyclopentyl. Okay, that would be impossible to do something like that, because you really just want to have 1 or 2 chiral carbons, because this may get really ugly, really quickly, and we really don't want it to be like that. We really don't want it to be like that. But you have to. We do look at the function of having an R versus the S. I don't know if you got to the carbohydrates yet. You've done carbohydrates in Dr. DeClo's class. That you have, they talk about the D sugars, right? Yeah, you talk about D sugars. And I'm assuming that you're looking at the aldohexoses. They're the 6 carbons. That you have, the first one is the aldehyde and the very last one. And what they look at is that the primary carbon at the bottom, you have all the sugars with that first OH to the right. And that was the D sugars. And the L for the amino acids. So there's many ways to make this harder, which I don't want to at this moment. So at this moment, all we're dealing with is 1 chiral carbon. And you to be able to assign RNAs. So my whole purpose of today, my whole purpose of now is that you know how to assign RNAs, and if you know how to name the compounds, then you should be able to do it. So I'll do one more, and then you guys can go, well, forget it. All right, so we'll see each other at, okay, so wait, sorry. I knew I wanted to give myself like a minute or two. We are doing a wet lab. The wet lab is extraction. An extraction, I don't know what the number is, but I think follows the conversation. I think there were students that still needed to do a melting point, right? Wasn't this a class that people needed to do a melting point?
Yes.
Okay. So what we are going to do is we're going to start finishing the melting point, doing the extractions. We have to find clothes to shoes and the proper gear, but then I'll see you all again online.